today we're going to start talking about the ways that we can manipulate material properties, or continue to talk about how we can manipulate material properties. And specifically, we're going to be talking about the role of dislocations in strength of materials. Okay, so you should know this by now from the midterm. What is a dislocation? Linear defect. Very good. So a row or column of atoms that are out of place. So linear defect is a row or column of atoms that are not in its ideal crystal location, structure. Okay? And a review, what is plastic deformation? Okay, permanent deformation. So deformation that doesn't return when the stress is released, and it's caused by the breaking and reforming of bonds. So when material scientists were looking at material strength, remember we talked about strength as resistance to deformation, right? So how much force is required to cause either elastic deformation or permanent deformation, so elastic or plastic deformation. So when material scientists were looking at the amount of energy or force needed to cause plastic deformation, they did some calculations. They say, okay, we know that we have a material, let's say it looks like this, and we push on this material like this. We're pushing it in two different directions, right? And so eventually it will deform. So initially the bonds might stretch, so you get elastic deformation, but eventually it'll deform and you get plastic deformation, so you'll get something like this. Right? Because you're pushing the material and causing, and they calculate, they say, okay, we're breaking 4 bonds in this hypothetical example, and we're forming 3 new bonds for the plastic deformation. And when they do this calculation, they realize the material, when you actually do it practically in an experiment, the material is much, much weaker. It's not requiring the amount of force needed to break the 4 bonds. And so they wondered what's happening, right? Why is the material so much weaker than we expect, based on what we know about how materials behave? And it has to do with dislocations. So if we look at the same material but with a dislocation, so this is if we had a perfect crystal, and then if we have dislocations, something like this, and let's say this is my dislocation, so my atoms are connected this way. Okay, and again, I push on top, and I push on the bottom. What will happen is that I am going to get breaking and reforming of bonds. But the dislocation is going to help me. How is it going to help me? Is that, okay, so I'm pushing this top part, and what will happen is that my dislocations the bonds will break and reform. And so in this case, I only have to break 1 bond and reform 1 bond, right? And then if I keep pushing, then eventually, so it's going to, and I keep pushing. So I keep pushing, but I'm only breaking 1 bond at a time. So I'm breaking 1 bond, reforming 1 bond, breaking 1 bond, reforming 1 bond. So dislocations actually make it easier for me to have plastic deformation, because it's giving me a way to break and reform the bonds 1 at a time, as opposed to if I had a perfect crystal, I would have to break all of the bonds and reform all of the bonds at one time. Okay, so having dislocations will give me a lower strength in my material, but it makes it easier to get plastic deformation. So it really depends on what you want. If you want a material that's very hard, but maybe when it breaks, all of it breaks, right, brittle, you might want fewer dislocations. If you want a material that is more ductile, can be bent without breaking, but also on the other side have a lower overall strength, then you might want more dislocations. So a couple of definitions. Slip is plastic deformation based on dislocation movement. So whenever you have something that looks like this, where you have a dislocation that's helping you have plastic deformation, this process is called slip. And a slip plane is the crystallographic plane along which the dislocation moves. So in this case, my dislocation is moving this way, right? It's moving in this direction. So this plane would be the direction in which my dislocation moves. So this would be my slip plane. And you may or may not remember there are two different kinds of dislocations. We talked about edge dislocations and screw dislocations. This is an edge dislocation. Screw dislocation has a twist to the way the dislocation is represented within the structure, but both of them can help move the structure. So both of them can aid in plastic deformation. So it doesn't matter if you have edge dislocation or screw dislocation or a combination of the two, they both will help in plastic deformation and also create a lower strength for the material. Okay, so we know that dislocations can help plastic deformation occur, lower the strength, so oftentimes we need to know the dislocation density. It's total dislocation length divided by volume, which is also equal to the number of dislocations per area. So usually you'll get something per meter squared or per centimeter squared. So dislocation density in a metal, a typical dislocation density in metals, it's around 10 to the third to 10 to the ninth per millimeter squared. So you have 1,000 to 1 billion dislocations per millimeter squared. So that's a lot, right? So for most metals, you have something on that order of magnitude. For ceramics, 10 to the second to 10 to the fourth per millimeter squared. Any ideas why in ceramic materials you would likely have fewer dislocations compared to metals? There are two reasons why ceramics might have fewer dislocations than metals would.
Stronger bonding.
Yes. Ceramics typically have either ionic or covalent bonds, which we know have localized electrons and very, very strong bonds. Right, so ceramics have stronger bonds, so they're more difficult to break and have, just more difficult to break because you have to break bonds in order to have dislocations. And related to the stronger bonds is the electrons being localized. So that means whenever you have a broken bond, you have an electron imbalance. Right? So in an ionic bond, you're transferring electrons. In a covalent bond, you're sharing electrons. And if you have a broken bond, then one of the atoms is at a higher energy state because it doesn't have the ideal electron structure around it. Whereas in metals, because you have delocalized electrons, a broken bond, the metals are still just as happy because the electrons are being shared with all of the metals and not attached to specific atoms. So having broken bonds or dislocations will also mean that there is more electron imbalance and higher energy state for the material, so it's harder to form those. In a metal, weaker bonds, easier to break, and even after you break bonds, you don't have an electron imbalance, so the metal is happy, even with a lot of dislocations. Then we talked about slip and slip planes. So slip happens more easily in a closed packed plane. So in FCC, the 111 would be a very good slip plane because that's the densest plane in the FCC. In the BCC you actually don't have a closed packed plane, right? Because BCC is not a closed packed structure. But you do have the 110, which is more close packed than the rest of the other planes within the BCC. Any ideas why close packed planes would be good slip planes? Why would there be a preference for slip to occur? So remember, slip is the movement of dislocations. And movement of dislocation is the breaking and reforming of bonds. So why would breaking and reforming of bonds happen more easily in a more densely packed plane as opposed to a less densely packed plane? Any guesses?
Is it because the atoms are closer?
Yes. The atoms are closer together, so there's less distance they have to move in order to break and reform the bonds. Right? You're pushing on the material to get the atom to move, and if the atoms don't have to move very far before they could break a bond and reform a bond, then that's easier. If you have to move the atoms further, then you have to put in more energy to do that before you can break and reform bonds. So the closer the atoms are together or to each other, the easier it will be to have dislocation movement, or easier it will be to have slip. And so slip happens because FCC is a close packed structure. Slip will happen more easily in FCC than in a BCC. Because in a BCC, all of the atoms are further apart compared to an FCC. So this is the reason why you have to learn about close packed planes. When we talked about crystal structures, right? It seemed like, who cares why? You need to know the way the atoms are put together. These are the different ways atoms are put together. Who cares why one plane is more closely packed than another? And why do you need to be able to calculate which plane has closer atoms to each other? This is why. It's because it actually does matter when you talk about material structure and material properties. So knowing the crystal structure, you can predict how easily slip will occur in the material structure, and you can predict the amount of energy will be needed to create plastic deformation. What is another crystal structure that has a close packed structure besides FCC? There are only two. So HCP, it's another hexagonal close pack. That's another crystal structure that has a close packed, where the atoms are very close to one another. Now I want to talk about, it's not that simple. The dislocations actually interact with one another. So dislocation interactions. You can have two dislocations. Let's say I have these two dislocations, something like this. And then I can have another two dislocations that look different. So I have dislocation here, and a dislocation here, and a dislocation here. If I have a dislocation in this scenario, this example, you can see that I'm putting stress on the region surrounding my dislocation. The atoms are out of alignment. They're not in their ideal crystal structure, so there's higher energy in that area, so there's strain here and here. This one I have strain here and here. In this case, if I were to try to move these two dislocations near each other, push them near each other, it's going to create a lot of even more strain, right? Because these materials are already kind of squished, pushed to the side. And if I were to try to move them together, the atoms will become even more out of place. And so these dislocations will actually act as if they're repelling each other. They don't want to be close together because by pushing them close together, you're creating even higher energy state within the material. This is very difficult to do. So if you're trying to push these straight dislocations next to each other, it will be a very difficult thing to do because of the strain fields around the dislocations want to stay apart from each other. In this situation, if I were to move this dislocation in this direction, and this dislocation in this direction, you can see how they might even cancel each other out. The two dislocations may meet and make a perfect crystal structure. And so these types of dislocations, when they're in opposite directions, may actually attract one another. So they want to be together because then they will actually reduce the amount of strain within the crystal structure. So remember, all systems want to go to the lowest energy state possible. By moving these two dislocations near each other, you're reducing the overall energy state of the material. By moving these two dislocations next to each other, you're actually increasing the overall energy state of the material. So this is difficult to make happen. This is easier to make happen. So dislocations actually interact with one another. And so the more dislocations you have, you may actually end up with too many dislocations and they can impede each other's movement. So we talked about initially that having dislocations is good if you want plastic deformation. But if you have too many dislocations, then they start to interfere with each other's movement, and you can actually end up with less plastic deformations. So harder, the material may actually become more difficult to deform. So there is some optimum number of dislocations. You don't want too many because they interfere with one another's movement and you get difficult to have slip. Or if you have too few, then you don't have enough dislocations to aid your plastic deformation. And then grain boundaries. So if I have a material that have grains like this is the orientation of the different grains. Okay, this is a material, and each one of these is a grain with the same crystal structure, but different direction, orientation, right? You can see how the slip planes would not necessarily be the same from one grain to the other. So let's say dislocations are moving along this way. They hit this grain boundary, and all of a sudden, they don't have a slip plane in the same direction anymore, right? The grain structure the orientation has changed. And so this boundary may also prevent dislocation movement. So grain boundaries can prevent slip. So would you expect, so you have two materials, one is a polycrystalline versus a single crystal. Which one do you think would be more resistant to plastic deformation? We assume that both have the same number or roughly the same number of dislocations. So they have similar dislocation density in the single crystal and the polycrystalline material. Which one do you expect will be more resistant to slip? Single crystal will be more resistant to slip. Polycrystalline, why? Why would polycrystals be more resistant to slip? Yes, because they have grain boundaries, and the grain boundaries prevent slip from happening or make it more difficult for slip to occur. So polycrystalline materials will be more resistant to slip. And the smaller the grains within a polycrystalline material, the more resistant to slip it will also be, because the smaller the grains, the more grain boundaries you have, right? So if you were looking at a microscope, you have 3 different microscope pictures that you're looking at, this is a single crystal. Everything's lined up in one direction. You have something that is a polycrystalline material with large grains. And you have another one with lots of little grains like this. Okay, I'm not going to draw all of them. But you can see this is a single crystal. Doesn't have any grain boundaries. Slip could probably happen as long as there are dislocations to help in that. This one will have grain boundaries that will prevent slip from occurring, but not too many of them. And this one has lots and lots of grain boundaries, so slip will be very difficult through this particular material. So polycrystallines will be more resistant to slip, make it more difficult to have plastic deformation, and the smaller the grains, usually the harder the material, but also more brittle. So stronger, harder, but more brittle. Yeah, do you remember all those terms? So strength, hardness, ductility. Ductility is the opposite of brittleness. Ductility means you can bend without breaking. Brittle means it's the opposite. It means you cannot bend without breaking. So glass is a brittle material. Ceramics usually are brittle materials, but metals can become very brittle as well. You can make a metal brittle by adding a lot of dislocations or making the grains very, very small. Hardness is resistance to local deformation. So deformation, again, is due to slip. And if you have very small grains, then you have high resistance to slip. Therefore, you're increasing the hardness, surface hardness as well. And strength is just how much energy you have to put in, how much force you have to apply to get the material to start to plastically deform. So we know plastic deformation requires the breaking and reforming of bonds. And that means you need movement of dislocations, which is also called slip. So if you have mobility of dislocations, hardness and ductility. So if I were to increase my dislocation mobility, would I expect my strength to go up or down? Would I expect my hardness to go up or down? Would I expect my ductility to go up or down? So how do we change dislocation mobility? So if we want to control the strength, hardness, ductility of a material, how do we control dislocation mobility? So let's say I want to reduce mobility because I want to make a stronger material. So you're a material engineer, you're giving this piece of metal, and they said this metal is great, but it is too weak. We need to strengthen the material, make it have a higher strength. What would you need to do? What are some of the things that you could do to make it stronger? How do you reduce dislocation mobility? What is it? Annealing. Let's talk more about dislocations and grain boundaries first. So you want a stronger material. Do you want to increase or decrease dislocations? Increase, right? Because you want to reduce mobility, reduce dislocation mobility. So you increase dislocation. You want to have lots of grains with lots of grain boundaries. You want to have more dislocations so that they can interfere with one another, possibly. In order to do this, like practically, how would you do this? Right? You have a piece of material, how would you actually reduce the grain size? And this is called working a material. A lot of times that when you work a material, you're actually doing it at a much lower temperature than the melting temperature, so it's actually often called cold working, or CW. You cold work a material. And I don't know if you've seen people making knives and swords, like in movies, right? They take a piece of metal, they put it in the furnace to heat it up. They take it out and they hammer, right? They hit it with something. Why are they hitting it with something? Well, one, they want to get it into the shape that they want it to be, but another reason why they're hitting it is they're working the material. By hitting it, you're increasing deformation. And that deformation will end up being increased dislocations and smaller grain sizes. you're breaking things up within the crystal structure. Okay, so that's called working a material, and that's the hitting of that metal, the sword, the knife, whatever, is giving it reduced dislocation mobility and higher strength. You put too much dislocation in it, the grain sizes become too small, it will actually become brittle because now the dislocations can't move. So then what do? They don't just hit it and keep hitting it, right? They do that and then they put it back in the furnace to heat it. They do this over, like, repeatedly. They put it in the furnace. The furnace, what it's doing is giving the material energy for the atoms to move around. The atoms, when they have the energy to move around, they will find their lowest energy state. So some of those dislocations will go away, and some of the grains will grow. And then they take it back out, they hit it some more, they put it back in the furnace, and they do this over and over. You know, most blacksmiths, the people who are making the swords, they don't know necessarily about the details of material crystal structure. It is just a craft that's developed over time. You know, somebody teaches somebody else, this is how you make a really strong sword. You do this 7 times, or you do this twice, or you heat it at this temperature with this kind of furnace, and then you hit it after it comes out of the furnace for 10 minutes, and then you put it back in. But over time, people develop a way of introducing and removing dislocations, growing the grain size, reducing the grain size, until they get something that they want. But what they're doing, the reason why they're doing it, is manipulating the grain size and the number of dislocations to get a material that's both strong but also not brittle, right, ductile. They want something that can bend without breaking. A stress-strain diagram. Okay, you have 2 stress-strain diagrams for A and B, and I tell you that A and B are the same material, same composition, same material, but you get 2 very different stress-strain diagrams. They're different because A has higher percentage of cold work. So it takes more force in order to start causing permanent deformation. Needs more energy for the dislocations to move. So it's stronger. B has less, so it's easier to get the dislocations to move. But B is more ductile, right? It can take more strain before it breaks. So we'll continue from here tomorrow.